And our next speaker is Ben-Nun from EDH, who will demystify parallel and distributed deep learning.
Yes, I would just like to start by saying that in this talk, I'm not going to focus on what we're learning, but more how we're learning. So I want to avoid these debates. So there is like one initial slide about what you can do with deep learning, and you all probably know that already. But it can go as crazy as program synthesis. However, that's not what I wanted to show. What I do want to show is, as someone who is actively tracking the research in the field of computation in deep learning, it's a very active area of research. So I've data mined a bit the archive website to see how many articles are being published in AI and computer vision. And turns out that in 2018, it's about 35 papers a day. So again, there are works that I may be missing. There are so many people trying different methods on different data sets and reporting results. And this is really interesting, Keith, what you talked about in the last presentation. Like exactly these sorts of things happen not only in networking, but also, for instance, in weather forecast. So these models are sort of destined to break, right? Because things change. If you were to train, for instance, like a deep learning network that would predict the temperature tomorrow. Okay, and I don't know, like temperature bases on many things, right? You base on like the pressure change and relative, like how the wind sort of flows. And let's say, I don't know, you build a new building at some point in a city, right? Then it's not in the observed parameters of the system, right? So the model will naturally break, right? So these models have to be retrained, I mean, to some extent. But okay, I'm not going to focus on that now, but we see the same sort of effects there also with training and test sets and climate change as well. Like, you know, if you train on certain years and then you would go and try the models on like years later, then you would also fail. So same things with the epidemic. In any case, so we've been trying to track this field, and I'm going to show exactly how we compute the process of inference and training in deep learning, what sort of communication is necessary when we do distributed computing, what are the approaches that are currently being taken, and sort of look at reproducibility as an issue, because reproducibility is one of those major problems that I personally have with the field. So I know most of you probably already know this, but I have to recap about supervised learning a tiny bit. So in supervised learning, the setting we have, assuming we have a data set and a model, right? So the data set has some samples that are labeled and supervised, and they're taken from this training set, but the training set is supposed to be an unbiased estimate of a full distribution, right, that we are not aware of and not know. We feed this through a function, right? That's the model for us. And in deep neural networks, it's just like a directed acyclic graph of operators. We come out, in the case of classification, with a probability distribution, right? And we want to compare that with the true ground truth label, and sort of we can use the difference between the two in order to optimize the weights in the network, right? And we go over the data set multiple times, maybe even mutating the data a little bit to be more robust to noise and other sort of artifacts. And essentially, this function has two main components, right? We have the network structure, that's the graph itself. In most cases, it's fixed. The other parts, the weights themselves, the parameters, that's what we learn, right? But we do like assume, in the case of machine learning, that we are training on the true data distribution and not the training set, right? So with the previous talk in mind, I am going to work under that assumption, okay? That we are training on something true. And so for loss functions, we have also many different, options that we can choose from. If we're looking at a problem like predicting the temperature, we might just go with a basic mean squared error. If we're going with trying to predict a classification problem, we might go with something like this. We don't want to go with something like this. It's not differentiable. This is a 0-1 loss. It's like sort of what you would think natively is like naturally. If the label matches, then you're good. If you don't, then you're not. But that's not continuously differentiable. So we use cross entropy, as we said just recently. But again, what makes this a deep network is that we have these operators. They're connected and they are applied in sequence. This allows us to do two things. So from the optimization side, this allows us to use the chain rule in order to compute the gradients if we want to do gradient descent. But it also allows us to do many interesting things with the computations and how we distribute them across the compute nodes. So if we take the data sets themselves, nowadays, especially in data sets like scientific computing, we have the forecast models. They can be hundreds of terabytes. YouTube 8 million, the video classification set, is 16 terabytes. And we have to access them in a pseudo-randomized order in order to train things. So we have that. The models themselves, depending on what you're training for, you may be training for a mobile device, you may be training a really huge model, 26 gigabytes, just to hold the parameters, and all the spectrum in between. But what's important is that these models are now the state of the art in accuracy, and they don't fit the memory of a single GPU up until very recently. Right, so this also poses an incredible challenge. When you have to train something, you have to think about distributed systems nowadays. And the whole process can take from a few minutes to a few days and a few weeks. You might want to retrain every day. So these are all things that we have to consider when we're doing the computation. And in essence, if you think about it, combining all these things together, deep learning is a high-performance computing, supercomputing problem. So I did mention that we're going over a data set. I just want to briefly go over the algorithm that we mainly use. So this is called stochastic gradient descent, right? We have to sample some element. We go forward through the network, and then we use the chain rule in order to compute the gradient. And then we update using some update rule, which there are many options for. Now, this does not seem very concurrent, right? In this sense, we just go through one element. So what we do is we sort of separate things into mini batches, right? We group the data into chunks, and then we can change the algorithm a little bit to work on those B elements at the same time. And as you can see, most of the algorithm doesn't change. However, there is this line 11 here. When we compute the actual gradient, what we do is we have to compute the average of that. So when we distribute this constitutes an operation that we call in high-performance computing all reduce. Right? It's a collective operation that you can distribute across the nodes. Another thing that is very important to understand, so high-performance computing is a field that is, it's very performance-oriented. And so if you say that you have some B elements here, obviously people will try to increase this B and try to train with more and more concurrency so that we can utilize the nodes as efficiently as possible. However, we have two issues here. So if we take the mini batch size, we freeze the number of steps that we take when we train. We see around 3 regions here. So there's an illustration, of course. On the performance side, the larger the mini batch, of course, the better we are. And we are limited by this communication in all reduce. Right? But the error itself is also different. Right? If you have too few samples that you're observing with a specific number of steps, then you will not get the result that you want in the validation set, right? And the further you increase the mini batch size, you also would start overfitting what we call on the training set, right? So this is, I think, something that may have happened in the CDC dataset of the weather, so of the flu, right? And a lot of research is continually focusing on increasing this B region to the right. So different methods, different optimization algorithms using second-order information, and so on. But we're still, this limit will always remain, right? We can move it, but not remove it, right? So this is important to understand when we're doing all these optimizations. Just to briefly show the trends over time, how we are computing deep learning, right? So we wrote a survey, a short read, very light, 60 pages. We're trying to see over the years what kind of architectures, what kind of systems we use for computing deep neural network inference and training. What we see is, ever since GPUs were a thing, they pretty much dominated the field. We're seeing sort of a balanced number of publications for specialized architectures. So ASICs, it seems like they're rising up, but in terms of publications, we're actually seeing this even trend. However, GPU is dominating.
TPU is specialized?
Yes, exactly. So TPU would be a paper, I think, around 2016. That's one of the specialized ones. Yeah. I think just now, yesterday, an Israeli company called Habana came out with another chip that does deep neural network training. So that's I have a slide for that, but I hid it for the purpose of this talk. In any case, what we're also seeing, and this is a more interesting trend because this is increasing with time, is that we have more and more distributed memory training, right? So you pretty much, as I said, the models are too large, and you want to train on larger data sets and larger batch sizes. So we're actually seeing that the majority of the papers today are using more than one compute unit, right? So they're using more than one GPU or more than one node. And so this is pretty much the standard these days. So very important. Now, how are they computing it? Two aspects. If we're using distributed systems, how many nodes are we using? So this is also an interesting thing. You can see here a weird sort of drop in the number of nodes. So does anyone know why this happened? So this pre-2013 one, this is work from 2012. It's called Disbelief from Google. Used 5,000 nodes to do some asynchronous SGD training. Nothing. They used 5,000 CPUs. Okay, so in 2013, Stanford came up. Yeah, exactly. Same, almost same workload. 3 nodes with 3 GPUs on each node. We got the same performance, and that's the explanation for the drop. However, we're again seeing an increase as the more we understand how to train, how to keep the validation accuracy high. We're seeing an increase in the number of nodes. I have a bit data, like I can extrapolate beyond 2017 here, and say that a full Titan supercomputer was used. This is around 16,000 nodes, if I remember correctly. Or sorry, yeah, or either 18,000 or 16,000 nodes used fully for the purpose of deep neural network training. And a year later, the winner of the ACM Gordon Bell Prize, which is like the highest award you can get from ACM on high performance computing, used the entirety of the Summit supercomputer, the first ranked, like the top supercomputer in the world, 27,000 GPUs, all for deep neural network training of a scientific computing problem. So we're using a lot of nodes these days, and also the median number of computer units is also increasing. Right? So that's also interesting. What are they using for the computation? So machine learning is it did not spark from high performance computing. So we would see in the beginning that people would use manual sockets, would use RPC. So a lot of works used whatever they already knew, Spark and those kind of methods. But as you can see, within over the years, we are converging towards a more decentralized communication interfaces like MPI that based on essentially highly reliable networks with low latency and medium to high throughput. I mean, yeah, obviously. And yeah.
Is this because machine learning researchers are starting to use MPI, or because HPC researchers are starting to do machine learning instead of weather modeling?
That is a perfect question. I mean, this is a bit of both, right? So these works, they're not just coming from the world of HPC, right?
If you look at the y-axis scale, you're talking about 18 experiments. It's not really a big sample size to.
These are only the works that refer to how to implement machine learning in distributed systems, right? But we're not just taking from high performance computing conferences and journals. We're also taking these are works from from machine learning venues, right? So Horavad is one of those libraries that you might want to use, or Glue from Facebook, and these are all using some form of communication that is either implemented as sockets or using MPI as a backend. And I'm going to get to the reason why this is important in one slide.
A way of asking the same question is, who are the authors of the 252 papers? HPC researchers?
Mostly machine learning. HPC researchers, they have a sizable number of works, yes. However, I think they're mostly, that's a good question. So these are only the distributed works, right? So these are 18 out of 250.
Yeah.
So these are works coming from both communities. So it also covers papers from Google from the recent NeurIPS conference, right? But also high performance computing. So yes, this is a bit biased. I would agree that that's true. However, when you do want to run machine learning on some cluster, what would you use? I mean, you want to sort of run. These will be pretty much the default backends if you want to scale beyond, I think, 16 nodes or so. Because performance-wise, this speaks. I mean, this performs better. But okay. So the reason why it performs better, again, is the way we sort of see communication in the world of high-performance computing is through performance modeling or in communication modeling. Right, so we take the computations themselves and we decompose them into a very, very fine-grained directed acyclic graph, which we call the computational DAG. And what we can see here is that we can look at all the operators, right, the operations and the dependencies between the operations. Again, very fine-grained. And we can study different things about it. So for instance, the total amount of work that we have is the number of nodes. And the depth would be, again, the longest shortest path between a source and a sync node. And the nice measure for, that we can recover from those two is the average parallelism. So the concurrency that you have, or the parallelism that you have across a certain layer would be, on average, the work divided by the depth. So that's more or less a very simplistic model to look at communications and parallel computing. And so I was mentioning before the fact that we have to average all the gradients in the case of data parallelism. The way we would do this is that there are different ways, right? We have to sort of take each node and its own contribution, average it with the rest of the contributions, and sort of scatter it to all the other nodes so that everyone is aware of the same gradient. Right, so the very simplistic way to do it would be sort of reduce and then scatter, right? So this is reduce broadcast sort of situation. Every two nodes sort of reduce the result, so you can see the communication happening here. And this has a certain time depending on essentially the depth here. You could also use butterfly patterns, which just exchanging data, or pipeline approach, or even a combination of these sort of operations called the Raben-Zeifner's algorithm. So this is an interesting approach because the time that it takes to perform this operation of all reduce is only a factor of 2 away from the actual lower bound that we can achieve on exchanging all the information, right? So why MPI is good for you in that respect is that it would have, or it does have, a system of heuristics, deciding when to use each of those methods and how to use each of those methods, and also the implementation relies on the topology of the network. So they do sort of do this multiplexing for you depending on many things that you as a programmer don't want to, or even as a like a designer of neural networks, you don't want to mess with this. You don't want to sort of interact. Whereas I'm going to show what the default sort of TensorFlow communication mode is, and it doesn't scale to these sizes as well as these methods. Okay, so again, I might be biased that I'm saying MPI is good, but it's also, like, in the absolute sense, it's better than re-implementing all those methods. These are methods that we've been researching in high-performance computing for, 3-4 decades, right? So we have really nice and robust frameworks that do all these decision-making processes for us. So, yes?
This is a basic question from a newcomer in the area.
Sure.
I'm always curious to know all this transformation of the networks. What's the effect on the performance, like on the precision?
I'll get to that. I think hopefully I have time to cover most of the things. I'm just going to briefly overview the techniques. But yes, you can always ask me questions. So we won't have a lot of time because I have to run soon. In any case, so let's try to break down what deep learning is from the computational side, like the principal components of deep learning. So first we have the operators themselves, what constitutes this network, right? For instance, a convolution. Then we have the network itself, which has a lot of opportunities for optimization. Then we have the training process, which has to read this data, have to store parameters. And finally, we have distributed training, which governs how we communicate, how we read the data in a distributed manner. And so, because there are 35 works per day, you can be very you can trust that any of these portions have been optimized to death, essentially. And so I'm again going to briefly overview some of the approaches. I'm going to try a new method in PowerPoint, so you'll see how it goes. And first, we're going to start with the operators themselves. Okay, so far so good. Okay, so if we want to compute a convolution, for example, that's one of the most computationally intensive operators in a deep neural network, especially when you work with 2D, 3D images, then this is where you would spend most of your time computing. So the standard ways to go would be to just compute it directly as a stencil. It's sort of like a neighborhood multiplication, addition, and the summation over the channels. However, it would also be nice to use a Toeplitz matrix formulation and take this whole computation, take the patches that we want to multiply and sort of unroll them into a matrix and keep the weights as they are, and sort of this is now becoming a matrix multiplication with some redundancy in the data. There are ways of how to save unloading that, but this increases the parallelism, and it's good for all these methods, like all these hardware architectures that are geared towards matrix multiplications. So that's one way that this is good for us. Another way, we could use the indirect methods like a basis transformation, FFT, like the convolution theorem. You could use Winograd transformation, which is a bit more specific, similar to FFT, but you have the freedom to change here all the weights here back and forth. So you have a different transformation for the samples, a different transformation for the weights, and a different transformation back, and you can compute like an optimal convolution algorithm, which is great, but the error also quadratically grows as you increase the size of the tile. So this is also very important to understand that different methods work better in different situations. And in the paper that I mentioned before, that we studied all the methods, we actually did the work depth analysis of which method is better where. So essentially you just have this sort of symbolic argument and you can just evaluate that and see. Right, so another thing that we're seeing more recently is changing the operator itself, right? So now we have the convolution. It's a very expensive computation. We can compute it in a different way, but we can also sort of modify the computation so that it would fit our needs, right? So one way to do it is instead of doing a convolution in n dimensions, we can start doing separable convolutions, so one dimension every time. So we save weights here, we save computation, and there are different ways to do this. You would sort of divide the workload and change those things, but what's important is that when you do these changes, you have to redesign the neural network around it. So it's not like you can just reset, change the convolution method to something else and expect that it will give you the same accuracy. So some of the works, what they do, at least these two down there, they change the structure of the neural network itself so that it keeps converging to the same thing. And this is a manual process so far, right? So at least so far in the slides. Right, so this is also very, annoying to the scientific community that you have to sort of change things, tinker around and see what happens. But what it does give you is an interesting reduction both in parameters and multiply adds. That these separable convolutions are what's mostly used now in the mobile device neural networks. So this is also interesting. Another thing that's interesting is maybe you can change the structure of the network to sort of squeeze and then expand. And this is good for two things. One, it's good for computations themselves, but also this is really interesting to see that you can use the neural network and use the layers as sort of like a compressor of sorts. So when you're doing your computations, you can actually reduce the data with these convolutions. And as an edge computing problem, this is very interesting because you can take like several portions of the network itself, compress it, and then say, okay, now I can send it over a network. So this co-design sort of process between software and hardware is very interesting. And these are the trends that we're seeing in the past 2 years, I would say. And yeah, I mean, feel free to barge in and ask questions because mostly people do. I know I'm not a native networking researcher. These kind of networks have different characteristics than you're used to, I know. But feel free. I can be stopped. Okay, so what about in between the operators, right? So I just mentioned that each operator on its own can be optimized. When we can, the next step would be to start optimizing in between. So one of the possible options to do this is to use a DNN compiler. These are really spiking in I think this year and the previous year. And what they do is they use the standard techniques from compiler construction. We take the neural network, we convert it into a graph of operations. We turn this graph into an intermediate representation which we can optimize. We transform it all the way until we get something to emit, like some code that we think is fast enough, and then we map it to the hardware. Right? So there are different approaches. We have TensorFlow's XLA, we have Facebook Low. They all sort of follow the same basic characteristics. Right? We have this graph to the IR undergoes transformations, then we map the code. Same with Intel's ngraph. We have different IR transformations, application, TVM stack, which is a more research infrastructure, and they pretty much all compete on doing the same thing. But this is very interesting that there is a sort of an underlying infrastructure here. And as for parallelism, I mean, there are different ways to take a whole network and partition it into multiple processors. Right. So the first thing that comes to mind is model parallelism. Right. We can take the network itself. We can partition it by the channels. We can partition it spatially. For instance, if it's a convolution, we take every quadrant of the image computed on a different processor. And all these things can be implemented. And for different networks, we would see different sort of balances. So obviously, when you are doing these kind of parallelism methods, you need to apply some kind of cost model and not just blindly say, oh, wait, the convolution is good to partition into 4 pieces. So again, this is great because as opposed to what I showed before, this is not increasing the mini batch size, right? So you're not degrading the statistical accuracy, right? You're just changing the way that the operators are computed. So you can distribute the parameters across the processors. You don't have to have this memory limitation. However, if you have a mini batch that is too large, or the samples themselves are a bit large, so this happens, for instance, in weather data, then you still have to copy it. Yeah.
I wonder if you could give a little more context about sort of where the constraints are. Like, are you limited by communications?
Oh, yes. So what I said before, the performance, sort of, you can increase the performance by increasing the mini batch size, but again, then this all reduce operation is the one that would eventually block you.
And do you see any role? First of all, do you see any merit for sometimes data parallel and sometimes model parallel approaches?
Yes, definitely. So for, I would say, very small data and very specific types of networks, data parallelism is great until some extent. I would just get to another slide and say that we just combine them all, right? So if you want a really fine-tuned computation, you have to do a bit of everything, right? So if the network is too large, you anyway cannot run it on a single GPU, right? So yeah, this
so
that.
Do you see any role for sort of lossy compression? If
Of course.
communications is a bandwidth.
Yes, that's another part of the. Yeah, that's the distributed part, right? Because this is just the parallelism in the network. It's not the part where you can change the training process in order to still converge with, in mind that you can reduce the bits. There are different ways to do this. I'll just get to it. Okay, so I think it's the next section. Okay, so in any case, another thing that's very annoying about these kind of networks is that you can see here. So as I said, convolutions. Sometimes you have to sum over all the channels. Then it means that every layer, every operator, you have to communicate all the results to the other processors, right? So this induces interesting communication patterns depending on how you partition and which operators you're partitioning, right? So mostly, in most cases, this is nice because we can still represent these communication patterns with collective operations. So reduce, scatter, all gather, all reduce, all of those things that we know from high performance computing, and we could still use them within the same node or between nodes, right? So this could be on a multi-GPU system, right? So, for instance. Okay.
Sorry.
Yes.
Quick question. So when you say complex communication patterns, what is your goal then? That all the data should reach all the nodes at the same time?
It depends, right? So if you are doing convolution, right, and you're partitioning spatially, right? So convolution has these dependencies on the neighboring sort of pixels, right? If you're partitioning spatially, you don't have to communicate everything, just the halo region, right?
So I think there's been a lot of work in the networking. This is me coming from networking community, right? There's a lot of work in the networking community which allows you to express these communication patterns in a very expressive manner. Just the whole, there's this whole thing that Berkeley people started on filters, and that actually allows you to do this very efficiently.
Right. So mostly also with collective operations, you can do the same thing, right? Reduce, scatter is exactly one of those examples, right? So yes, for most of the partitioning and the layer types you can, not for everything. Sometimes, I don't know, I'm not sure if I have an example ready, like batch normalization. In some sense, you have to at some point do an all-to-all communication, which can also be optimized, right? If you use the right calls to the right, if you just time all the operations right, all the networking calls. However, there's a simple way of sort of partitioning the network, which would be pipeline parallelism, just partition by the depth, right? That's much easier. You have those fixed communication points. So, for instance, you can take this network and take, like the first 10 layers go to the first processor, the other, and the third would go to the other processor, right? So we have, again, this nice added benefit that we can distribute the parameters across the processors. We have a communication pattern that is very fixed. We don't have to, we just have to transfer all the data forward, so that's easy. And it's only between two peers, right? So we only pass it in one direction, and we can use it to also, increase the computational concurrency, right? So we run the first part of the mini batch, then we transfer it to the second, then the third, and then we have to do the backpropagation, so this goes in the other direction. However, you can see here that we're not getting any concurrency, right? So if we take the whole mini batch and we sort of send it through the network, we're getting just the idle time, right? This bubble. But that's known also from other problems. So what you would do in these cases is called a micro batching. You take the mini batch and you subdivide it into smaller sub batches. Then you can still microprocess. You can still process concurrently. However, you still are left with the same bubble, right? So that's not something that you can get rid of unless you would change the training algorithm to sort of be inconsistent with the parameters. So you can say, oh, I'm allowing the parameters to backpropagate before we even start, like before we feed the next part of the micro batch. So you could do that. But that also induces some degradation in the accuracy eventually. So the final one is what I said before, data parallelism. You take just the samples, you distribute them across the processors. It's very easy to implement. This is one of the major benefits and why this is the mostly used way to parallelize deep neural networks, is that with any framework, with anything, it's so easy to implement. You just run the same model everywhere, right? When you backpropagate, you just have this all reduce or whatever communication operation in the end or in between. So you can do that. However, in some cases, this is not, it doesn't even fit the single device. You have to duplicate the parameters. And as I said, if you go too large, then you affect the generalization, right? So as I said before, what you actually do is a bit of, why not both, or why not all three, right? You can just combine pipeline parallelism with data parallelism and model parallelism all at the same time. For your specific neural network architecture, you can find sort of an optimum for this, right? However, this is not something that is like readily available in any framework. You have to pretty much do this yourself these days.
When you say do this yourself, this is sort of like a trial and error thing based on the data, right?
Well, most of these computations are very, they're called data oblivious, right? It doesn't matter what image you feed in, the computations would be pretty much similar.
Right, but are there guidelines for what the...
Well, there is a paper from 20...
look like, or what...
Yeah, there is a paper or a tech report from 2014 that says, I think this is the one here, that says, where you have a lot of computations, do data, do data parallelism. When you have all the parameters, do model parallelism. However, this is not enough. I mean, this would be great for a very linear monolithic network where you have this separation, where you have different kind of operators. But today, the networks are more modular and sort of built differently. So you could potentially, very easily, build a cost model that would estimate how each partitioning would work for you. Right? We know some aspects of the networking because we assume this highly reliable interconnect. So, yep. And we know the computations themselves, right? We may not be able to predict exactly how they will perform, but you could run benchmarks and sort of tune this, right? So in the large systems, you don't see a lot of papers with hybrid parallelism, and they're usually reserved for the very large companies. So Microsoft did something, it's OSDI 14, where they combined all of these things to train on a huge network, on a huge cluster, and Google did that, but it's really hard to do this as an end user. Right, which is what I see now as one of the things that one of the challenges in machine learning, deep learning that we should sort of address, right? Yes, but these are sort of what we do within the networks themselves. What we could also do is try to think of different ways to optimize this fixed part, the network, right? As I said before, you can change the convolution to be more efficient. Why not try a more, let's say, systematic method of finding a better neural network? Right, so you could use reinforcement learning to do that, to tune hyperparameters. You can use genetic or evolutionary algorithms in order to train the network structure. And obviously, you would use some characteristics of the neural network, for instance, that it's sort of modular, right? So you can train each module separately and sort of increase in the hierarchy. And there are many different ways to do this. I mean, this is now explored. Most of these methods also waste a lot of computations. So the works in 2018 and 2019 are also focused on trying to find some model-based optimizations for this so that you would not spend, let's say, I don't know if it says here, but okay, so the state of the art for mid-2018 for this image classification data set has really interesting results. However, it used, I think it was 2,000 GPU days in order to train. So that's a lot of computational power that you could obviously improve. However, what's nice about this is that you can tune the network, you can tune it for accuracy, right? You can tune it for validation accuracy, which is also a problem on its own merit, right? Because we're saying, we're now sort of overfitting the validation set, right? But this is happening. I mean, these are the papers that we're seeing nowadays. So same issues that we had before. But you can also tune them for reducing the number of parameters, reducing the number of multiply adds, right? And that's what they're doing. So for mobile sort of devices, that's a great way to recover what is an interesting or a better way to construct the module so that they fit. So as for distributed, I mean, this is the main part here, right? So how do most of the frameworks, most of the approaches go with respect to distributing this across cluster? Right, so we have this network. We assume data parallelism in this situation because model parallelism and pipeline parallelism are orthogonal. Right, so the way that you might want to do it is, well, there are three axes. One of them is how centralized do you want the process to be. Right, so the way that goes by default in TensorFlow, I think up to today, is using a sharded parameter server. Okay, so parameter server, you have every agent, they're working on a different part, like different samples. They're transmitting their gradients into that. This is, it's not essentially one node, it's more. And this server receives all the data and transmits back new weights. This is great, but theoretically, also it doesn't scale with respect to how many nodes you want to use. Right, so this, from my personal experience, works well up to 32 nodes. But you want to extend beyond, depending on the interconnect, obviously. But if you want to extend beyond, then the decentralized approaches work much better, right? Where you have training agents, and they're doing this collective operations. As I said, like they communicate with each other without having this one management sort of infrastructure, where we can use the Rabin-Zeifner's algorithm or whatever you're given, or you can also use, RDMA and other forms of remote memory access. You can use the topology, you can use different types of collectives for different types of operations. So this is, MPI is sort of good for you, but I'm not here to advertise MPI. Yes, I was against MPI in the beginning, but I have been converted because it's nice. I mean, okay, anyway, so there have been other points in between that spectrum of centralized and decentralized, right? So you can take a parameter server and you can make it hierarchical. You can sort of tune how much you're communicating with respect to the problem itself. So this is one sort of axis, right? Centralization. The other one is the consistency of the model. What I said before with pipelining. So one of the sort of issues that we have is that we are we're capable of computing everything with this synchronous SGD, right? So we have to transmit the gradients, but then you might have different nodes that operate at different rates. Network can be imbalanced, and so also the data sets can be imbalanced when you're doing video classification. Some videos are longer, some videos are much shorter. This would hinder your way of scaling up. And so what you could do is go asynchronous. So you can go completely asynchronous. Right? You can remove all the locks and say everyone transmits a gradient whenever the parameter server sort of finishes processing it. It just sends back weights, right? And you can have slow nodes operating at different rates than the other nodes. However, as the paper shows, even theoretically, it doesn't converge unless you assume a specific delay, like a specific maximum delay, right? So this would be the staleness of the gradient. So for this, there are other approaches that have been proposed. For instance, stale synchronous parallelism, which essentially does what we say, just enforce that the staleness would be up to a certain rate. So they say, okay, too large, parameter server would just either ignore it, scale it down, wait, like just block the training agent, and so on. So this works great in a parameter server model because you have the freedom to go through all this spectrum from consistent to inconsistent weights across the nodes, right? In decentralized, that's a bit of a tougher situation, right? So synchronous, as I said, we have this all reduced collective operation, but in stale synchronous, a bit harder. You would have to sort of encode into the collective exactly where each node is at. I mean, you would probably run, I don't know, a vector clock or something like that in order to sort of understand, because what you're doing is you're training, and there is a very specific time sort of definition, right? With the number of samples that you've seen, right? The steps in this optimization process. So you could use that and sort of tune the operations, or you could go completely asynchronous with different approaches. You could fix a communication graph. So for different topologies, that might be better. Or you could go gossip, right? So that's like a gossip-based asynchronous SGD is possible, right? You just transmit. However, you also have the risks of using gossip algorithms. If, for instance, you just transmit over links, over random links, and you have obviously the slowdowns that come with it. So you could also go a bit further into the inconsistency between the agents. You can also say, I don't want to communicate every step. I want to communicate every couple of steps. But instead of doing standard averaging, we may want to use something like a bit more sophisticated type of averaging, like more elastic average, which takes into account like some sort of physical state where you have the average, you have all the other nodes, and you sort of elastically find a point that makes sense. So this is one way to do it, but there are more obviously in the paper. Or you could just let go of communication during the training process completely, right? You can do ensembles, where you just train the same model, different data or different instances, and just average the results in the end, right? So that's completely embarrassingly parallel in that sense. As for the communication itself, so because SGD is stochastic gradient descent, is a robust process, right? We're doing some kind of optimization. We can reduce a lot of the aspects of what we're transmitting, right? So if we're transmitting gradients or if we're transmitting weights, in the case that I've shown before, then you could, for instance, take the weights and decompose them so we don't have to send everything. You can quantize, so you can send less information for each weight. You can sparsify, so you can not send all the weights, right? So this is the quantization. There are many ways to do it. They even go down up to transmitting 1 bit per parameter, and this still works under one assumption, and this is what's read here, that when you're doing this, you have to think of two things. One, when you quantize, you have to do it in a way that in expectation would be similar to the actual training, so we have to do like stochastic quantization. And the other thing is that when you do have a difference, when you're not sending some information, the residual must be accumulated locally. So you have to sort of remember that and keep transmitting the information. Otherwise, it doesn't converge. That has also been proven. As for sparsification, you can take different methods to do it. For instance, you don't want to send gradients that are too small, or you only want to send the top K gradients. But still, again, as long as you accumulate the omitted gradients locally, you can still converge. And we have one of those works that we did. So we created another version of a collective operation, a sparse collective. So this is called Sparse Ml, where each agent has its own sort of weights that, or sort of gradients that you want to optimize. Right, so in that sense, they don't have to match, right? Different samples mean different gradients are active. So if you implement the standard collective operations, as I said before, like the reduce scatter or the other methods, is butterfly, then you can exchange the information and you could continue reducing with the sparsity in mind. And so this works. As you can see, the more steps you go, the denser you become, because in essence, you have different data set or different samples and different gradients, so you can imagine that this would go up over time. However, this is enough to scale up to 128 GPUs in a true Microsoft production environment. We managed to reduce the training time from 2 weeks to 2 days and achieve the same quality, which is also great. And in that sense, the higher the latency in the network, or the worse the network is built, the higher the speed up in these situations. That's exactly when you would want to apply these sparse all reduced methods. However, we're going here in this work through the CPU in order to do this, these sparse all reduces. What I would imagine as an interesting way to continue is to use programmable NICs, for instance. That's also an interesting approach. So what we published 2 years ago is called SPIN. It's sort of, you can imagine it as a CUDA for NICs. Essentially, yeah.
I feel like I have to give you a hard time here.
Sure, go ahead.
What was the problem with normal networking? I don't see how programmable NICs is at all called for here, unless you're hitting up throughput limitations of the software to copy stuff from Ethernet to GPU.
We are.
Doesn't matter.
Okay, so I would like to sort of draw the situation. So deep learning is very resource hungry, and you can trust that people implemented it so that you use all the resources that you have.
I'm not big
So,
on trust.
Right. Okay, so don't trust.
How many gigabits per second do you want, and how many are you getting, and how many do you think the hardware is capable of?
Depending on the model, depending on the data, we're actually seeing it. We're seeing that the communication is what's stopping us, right?
But
we pipeline all the communication that we can, right?
People in this room have 10 gigabits per second working using the CPU.
We have 40 gigabits per second.
People in this room have 40 gigabits per second using the CPU. So what possible benefit can you get from
No, but the CPU is already utilized for something else. That's what I'm going to say.
all of them?
Yes, that's the problem. So what they're doing is you have to read data from the data set, from a hard drive, decode images, for instance, augment the data, flip the images, I don't know, add some noise. read this into the neural network. The neural network is operating, but while it's operating, you can start reading the upcoming data. So that's what you do. You spend most of your cores reading and pre-processing data on the CPU.
Are you not doing that on the GPU as well?
Yeah, some, yes.
On the GPU, isn't your CPU free?
No, but then the GPU is also computing the function, right? They're evaluating the function and computing gradients, right? That's where most of the time is spent. However, you can keep loading data, like you can keep loading samples, right? And keep copying it to the GPU at the same time. So you have at least a few resources that you can use. One, you can use the parallel I/O, right? You just read from, you just have random access to a parallel file system in each of those nodes. You're reading them, you may cache them locally on an SSD, you may not. You read from that SSD, you process that data on the CPU. While you're just, you transfer that to the GPU, you compute, but then you can start processing more.
I think what Keith is trying to ask, is your bottleneck in the network, or is it reading from the SSD and doing this pre-processing?
It depends on the network and the model, right? So sometimes, I think the latest Google work, saying that the I/O is the bottleneck.
Just like reading from a 40 gigabit NIC into wherever is so easy, it consumes such a small fraction of a core.
Yeah, but I'm talking about this.
It's hard to believe you could get a substantial benefit by offloading that to a...
I'm talking about a sparse all reduction right now, right? So you have to do a top K, you have to do this concatenation of the sparse data, you have to retransmit it to the other nodes, and you have to accumulate the local gradients.
Let me ask you
Let me get to that
Is
point.
having the algorithm run on the NIC better than just adding one core to the machine?
That depends. I mean, having one more core on the machine, you would still...
I mean, if you have 32 cores on the machine, is this going to be any better than having 33 cores on the machine if you get the NIC involved?
Well, there is some latency involved when you read back into the memory, right? You have to go through the CPU and you have to go back to the memory, right? So
that's very, very low. I mean, I don't give you a hard time, like, but
is it very low?
But
okay.
But I think you're doing distributed computations, right?
Right.
So I don't understand why you say all CPUs are busy, because you can just take 2 CPUs out and include 1 extra machine in your distributed computations. So that argument I don't understand, but I don't want to push back.
So
why are you so nice to him?
No, don't be nice to me. I wasn't nice to anyone else. Yes. No.
Understand why? Okay.
I agree with you.
Yes. So 40 gigs you can't do on a single core, right? You don't use a single. You need, unless you do very low level optimizations, right? You will need to.
No. It depends on packet size. This is not a case where you're sending 64-byte packets. You can do 40 gigs of 1500 byte packets on less than a single.
Using DPDK.
Yes.
But not using kernel code. I think they're going to the kernel. No, to the kernel you can't do 40 gigs.
So why do they have to go through it? Like they can, and also like on
that's why I'm not pushing
previous
back.
They can do that.
So that's why I was not pushing back. That maybe if they're going to the kernel, 40 GBps might take 2 cores, 3 cores.
I think on FreeBSD it apparently takes less than a core.
Because Netflix claims that they optimized it to that point. Means that because that's their platform.
I would be very surprised if using traditional kernel code and 40 GBps you can do it in a single core. I would be very, very surprised.
So I just want to tell you that FreeBSD's kernel implementation is NetMap. So if NetMap can't do it, so if NetMap can do it, then we're back to that same problem, right?
Yes. So I would just like to again talk about latency in the network. Right, we're talking in the latest supercomputers we're like 2 microseconds latency between 2 nodes, right? And the PCI Express bus is 1.5 microsecond latency just to transfer this information to the GPU, for instance. So we would like to conserve as much as we can, right? So we're at the point where we're optimizing pretty much everything.
People talk about latency. Now I will not be nice. Okay.
Okay, don't be nice. Yes. So by the way, this is not done. So yeah.
1.5 microseconds.
Yeah.
Right? How long does your application run, and how much do you spend in the network itself?
That is true. That is true.
People who talk about latency in terms of
makes sense.
Optimization, that's not a good idea.
Not true.
Okay, let's thank the speaker. No.
Yeah. Yeah. So okay. I will skip that part where I say that it's better to do a non-contiguous data transfer using the NIC itself. Right? Even when you're on the data path, you can still attain some speed up.
This is the part we're most interested in. Why would you skip it?
Right? Because we were just discussing it. It's not worth it, right? Okay. No. So what I'm saying is that that's one of those things that, well, we have 2 elements here. So first of all, we don't have to involve any of the parts that process the deep neural network in the communication. Right? We have the gradients, we have to transmit them, we can store them locally, and we can accumulate them later as part of our sort of pipelined approach and copy them to the GPU. It doesn't have anything to do with the process of the optimization itself. Right. The other part is that we have some kind of input buffer. We want to process it very lightly to sort of find the threshold from which you don't want to transmit that. So you transmit indices and you stream indices and data that you deem to be important, right? It's just one comparison, right? We're talking something that you can still stream process, right? When it reaches the other NIC, you don't have to go back all the way to the CPU to store it into memory and sort of add to the specific locations. This is just indirect access. This is exactly why you would use a programmable NIC. Yes?
So I'm confused, but one problem that I always have with this particular thing is how do you do pushback? Because the problem is if you're streaming, if I start streaming data and the other side isn't processing fast enough, you need to do the equivalent of pushback and have me stop sending data. So I think these streaming examples always look good when you assume perfect pipelining, but you have a CPU involved. Your CPU does not have deterministic timing.
Yes, but we can hold off on the process. We can still store it and copy it with the rest of the data,
memory,
right?
So if
right.
the CPU gets slow, when the moment you start saying you can store it, you're assuming that you have sufficient memory to store everything always. Is that the assumption that you're making? It's fine if it's an assumption.
Not necessarily. Yes, you're right. For the large models, you don't. But you can tune with model parallelism, and you can have that assumption again. Right? You can say, okay, I just subdivide the network across the nodes and have that.
But you have to know a priori how the CPU slows down to know to subdivide it, right? So, so one way to look at it is pushback requires logic. Where is that logic executed?
Mm-hmm. So I would also say, by the way, that if you're using model parallelism, you can use the NICs to sort of redirect the messages to wherever you want. You don't have to do the standard collective operation. You can do a different, sort of routing process for that takes the model parallelism into account. But okay, I mean, in the interest of time, we can take this discussion offline. What I wanted to say is that, in essence, this is an interesting sort of problem, and we talked about reproducibility for the past 50 minutes. There are different ways why we cannot reproduce every workload. You cannot even represent the same network on different frameworks. The same data set. Some data sets are called TF records, which has the TensorFlow in them. So you can imagine that this cannot run on PyTorch, for instance. And the training algorithm and distributed training, that's completely there is no standard behind it. So one of the things that we are doing is sort of trying to standardize deep learning in that sense, to divide all the important parts and create a meta framework, like a framework for frameworks. So just the interfaces, the raw, if you have an operator, all we have to do is implement the forward and the gradient. And for instance, what we give you is automatic gradient checker with numerical gradients or something like that. Networks, we use a standard network representation, which just have, it's a graph, right? Executor just have this inference and backprop, which could be mapped to, I don't know, CPU, GPU, or an FPGA. This inference could have some compilation involved before, right? Then you have to read from some data set, you have to sample from the data set. So all of these sort of interfaces that are mostly used in all the parts that we've talked before, like the operator, the network training, and even distributed training, where you have the consistency, the centralization, how you sample, how you partition the data. That's also very important, right? So I'm not saying that there is some way that we should do it. I'm not really claiming any of these things. I'm just saying that we should be able to benchmark each and every one of those methods separately from the others, right? So if we want to replace the distributed optimizer, we don't have to replace how we compute the network itself, right? So this is what we did. We created something called a recipe, like we have the fixed definition, which is what is the data set, what is the network. You can sort of define that. We can have the mutable definitions, how you want to train it, how you want to distribute it. And then you have this acceptable metrics. For instance, I want the test accuracy of 93% at least. And that's something that is qualified to sort of compete. And everything is well defined. You can have your own implementations of everything. So we have this TensorFlow and PyTorch. You can just replace the framework by just replacing what FW is, right? That's the benefit of having one infrastructure that sort of understands what is deep learning in essence. I'm not going to go into all the details. What I'm saying is that you could implement any of the gradient compression methods in general, and would be easy. Just to summarize, well, we're talking about some high performance computing problem. We're using all the resources we have. We're getting to the point where I/O and latency is the issue that we have to tackle. And we could change many of the aspects. It's a very robust process. We can relax the consistency of the parameters. As I said, like every agent can have its own copy. We can relax the accuracy of the parameters, and we can still converge if we do things in the right way. But the main objective is always to generalize, right? So we have to remember that you don't just want to tune for performance. You have to keep in mind that you have to generalize. But yeah. So if you want more information, there's this work. That's the 60-page read. And there's the other work. That's less of a read. I think it's an 11-page read. And what I wanted to say, so I'm sorry that I'm wasting a bit more time, I just wanted to have a call to arms on having more data sets, right? Because all the data sets, all the benchmarks nowadays, they have this ImageNet, they have CFAR, they maybe have some one tiny reinforcement learning problem. We need more relevant data sets for scientists that, yeah, we need more relevant data sets and time series for things that are important for scientists in many different fields. Maybe network traces are a very important data set that we want to train on and see how different methods react. Yes, but just saying that, you wanted to say something? It seemed like you wanted to say something. I don't know.
I think
You're making a face when I said more data sets, and I was like, oh, okay.
Oh, well, I just gave a talk about how
Yeah, I
data
know.
set is the wrong thing to think about.
Maybe we need a different approach, right?
Let's thank the speaker.
Yeah.
So we'll meet here again.